If x and y are independent random variables with PDFs f of x and f of y, then z, the sum of x and y, is also a random variable. We can easily find the mean and variance of z. But what about the PDF of z? In general, even if x and y are independent, the PDF of the sum is not easily determined from the individual PDFs. For example, if x and y are the results shown when a 6-sided die is rolled, then x and y individually have a uniform PDF, but x plus y has a binomial distribution. Unfortunately, if x and y are independent normal random variables, then their sum is also a normal random variable. It's unfortunate because it means there's nothing to be done. And so we have an important theorem. Suppose x and y are normally distributed with means and standard deviations, then the sum is also normally distributed, where the mean is the sum of the means and the standard deviation is the square root of the sum of the squares. Now, remember the standard deviation is also the square of the variance, and so instead of writing our standard deviation formula, we note that if we square it, we get, and so here we have the variance of the sum is the sum of the variances. So, for example, a company's quarterly profits are independent and normally distributed with mean 8 and standard deviation 24. Let's find the probability that a company has a positive profit during a given 4-quarter period. So remember, means and variances add. So the mean for a 4-quarter period will be the sum of the means in the individual periods. And so our mean is the variance will be the sum of the 4 variances. So remember, the variance is the square of that standard deviation, and so the variance will be, and the standard deviation will be the square root, which will be, and so the sum of the 4 quarterly profits will be normally distributed with mean and standard deviation. So if the profit is 0, well, that corresponds to a z-score of, since our table only extends to 2 decimal places, we'll convert this to the decimal negative 0.67. And so the probability the profit is positive will be, so let's go ahead and graph that region. It's the area to the right of negative 0.67, which by symmetry is the area to the left of positive 0.67, and we can look up that value on the table. Or let's consider claims at an insurance company and assume they're independent. In year 1, claim amounts have a normal random variable with a mean and standard deviation. In year 2, claim amounts are modeled by a linear function of this random variable. Let's calculate the probability that a random sample of 25 claim amounts in year 2 will average between 100 and 110. So let's find the mean and standard deviation of the individual claims. Well, remember, the mean is the expected value. The expected value of y is the expected value of that linear function of x. And we can remove that factor, and we get, and so our mean is, the variance will be the variance. And remember, adding a constant doesn't change the variance, but multiplying by a factor will introduce a factor squared, and so our variance will be, and so that means our standard deviation will be. Now if I take 25 claims, the average will be, and so the mean will be, meanwhile, the variance will be the variance of this function. And again, that's a constant multiplier, so it comes out as a square. And since all the variances are the same, this is going to be 25 times any individual variance. Well, we know that variance, it's the square of the standard deviation. And so our standard deviation will be Now, because we want the mean to show up on an interval, we'll find the z-scores for the endpoints of the interval. And so this is the region between negative 1.73 and 0.19. Well, that's all of the region to the left of 0.19, from which we'll remove the region that's to the left of negative 1.73. Which by symmetry is the same as the region that's to the right of positive 1.73, which is complementary to the region that's to the left. And so we can look up those probabilities and we find